This topic is topic 9 about drawing inferences, and it refers to chapter 7 in the Adams text. So as you know, we draw our sample from a population, and we're going to talk now about how we can take data from our sample and infer back to the population. So we'll begin today with a review, and then we have a lecture in 4 parts. We have part A, comparing a sample to a sampling distribution. Part B, rejecting the null hypothesis. Part C, type 1 and type 2 error. And part D, interpreting statistical significance. So first, the review. If you are joining in the online only session, this won't have the richness of discussion as it will in the face-to-face session or the Zoom session, but I hope that you can watch the video and consider the questions at the end. This is a very short video that's just teasing out studies in stereotype threat. And it's 6 minutes long and it's quite interesting. And when we're done with it, we're going to talk or consider these questions. So what is the population of interest? What is the independent variable and the dependent variable? How is the dependent variable operationalized? And what variables were controlled? And then we'll refer a little bit to these studies later in the lecture. Part A, comparing a sample to a sampling distribution. How can we tell if a dice is loaded? So first, let's figure out what possible outcomes we could get from a pair of dice. So there are a limited number of results that we could get if we roll these 2 dice and sum them. So could we get a sum of 1? We couldn't. It's not possible. The lowest we can get are 2 ones, which equals 2. So the red dice gets a 1 and the black dice gets a 1. We could get a sum of 3. We have 2 possible ways. Red dice could get 1, black could get 2, and red could get 2, black could get 1. That's it. A sum of 4, we have 3 ways. Red could get 1, black could get 3, red could get 3, black could get 1, or each of them could get a 2. And we continue like this. We see that a sum of 5 has 4 ways of achieving it. A sum of 6 has 5 ways. A sum of 7 has 6 ways. And from here we start to go down. A sum of 8 has only 5 ways of achieving that sum. Sum of 9 has 4 ways. A sum of 10 has 3 ways. A sum of 11 has 2 ways, and 12 has just 1 way. So the probability of getting a 12 is equal to the probability of getting a 2. And so this is like our sampling distribution. So let's take a look at this in a little different way. So this is the sampling distribution that we put together from the previous page. This is what we would expect if we had a large number of rolls. So to repeat, if we roll a pair of dice again and again and plot the sums on a graph, we would expect that after many rolls, the distribution would resemble this distribution, with the highest frequencies or the highest number of rolls at 6, 7, and 8. And at this time, I'd like to invite you to roll a dice and plot them. When you get a sum of 2, put a mark here and continue to plot them all the way up. And this is a nice little dice rolling, not rice doling, dice rolling app that you can try out. So this is like an example of what you might get. It won't probably be this perfect. It'll probably be different from this slightly. But the more rolls you do, the more likely your distribution will closely resemble the distribution behind it. So the first distribution is the sampling distribution, what we expect to see. And the second is maybe what you get after rolling a large number of pairs of dice. So this is the expected distribution, the sampling distribution, if everything is normal, if we have a distribution that's not expected to be different in any way, the dice are normal, there's nothing that's expected to be different. If the dice are loaded, we might expect different results. Or if we think we can teach someone to roll in a certain way, we might expect different results. So imagine now that we have a theory that a particular skill of mental telepathy could improve the number of high dice rolls. So now you're going to teach the skill to people, and then you're going to have them roll the dice and plot the results on here. Every time they get a 12, you're going to plot it. If they get an 11, you'll plot it. If they get a 2, you'll put a number, and you'll do it for a large number of rolls. Imagine that this is the distribution you get. We expect the distribution to have the highest peak in the center here, but now instead we are having a distribution where the highest numbers appear to be in the sum of 10, sum of 11, sum of 12. We call this a skewed distribution because it has a long tail, and we might think that maybe our skill of telepathy is effective. So this is kind of an example of what we're doing with statistical tests. We're comparing our result with what we would expect if nothing were going on. So the normal distribution has some characteristics, and we can define these characteristics and predict what results would be expected. So for example, we put together standard deviations. So what this means is how far apart are the points from the center mean. The center is the mean, and the normal distribution is symmetrical on both sides. And then we kind of put a marker here at about this midpoint where it begins to flux down at this certain curve level, and we call this 1 standard deviation, and this is -1 standard deviation. And we know that 68% of the points in a normal distribution are going to fall between this -1 and +1. That's the characteristic of a normal distribution. We can see we have the 2 marker, 2 standard deviations way down here in the tail and down here in the tail at the point where this curved line begins to go to a more horizontal direction. You can see that the lines are evenly spaced, and these are called standard deviation, and we know that 95% of all of the values are within 2 standard deviations of the mean. And we know, well, these lines, even though you can't see them, these tails of the distribution go into infinity in both directions in a normal distribution. But 99% of the values are going to fall within 3 standard deviations of the mean, 99.7%. So to get a score that's higher than this or lower than the -3 would be pretty unlikely. Only a 0.3% chance of this occurring. So we use these rules of odds to determine whether a result we get is expected or not. So let's think about this p-value a little bit more. So the p-value is the significance level the researcher wants to achieve in order to find that the data supports her hypothesis. She determines the p-value based on how much confidence she believes she should have in her conclusions. We'll talk a little more about this when we talk about type 1 and type 2 error. So if the researcher sets the p-value or the significance level to 0.05, then she wants to have less than a 5% probability that her result could just be by chance. If she sets the p-value to 0.01, she wants only a 1% probability that she could get such a result by chance. So just to put this in terms of our dice roll, we all know that it would be possible for someone to roll a pair of dice and get a 12, and then roll it a second time and get another 12, and roll it a third time and get another 12. We all know that's possible, but it's not very likely. So the researcher calculates the probability of that happening and then decides, okay, if this mental telepathy worked, then what odds am I comfortable with that just didn't happen by chance? So in research studies, we would look for something like this. P is less than 0.05, meaning the probability of achieving this result is less than 5%. Or P less than 0.01, the probability of achieving this result by chance is less than 1%. So I'll give you an example from our studies in stereotype threat. So this is taken from the Steele and Aronson study, one of the, I think it is the foundational study in stereotype threat. And you can see I copied this right from their paper. And it says the adjusted means are presented in figure 2. Here's all the stuff it's hard for you to understand, but it says planned contrasts on the adjusted scores reveal that, as predicted, blacks in the diagnostic condition, who were threatened, in other words, performed significantly worse than blacks in the non-diagnostic condition. Then this little t just means that's the test they use. 35 means that's it's the degrees, it's close to the sample size that they had. They actually would have had 36. 2.38, that refers to their score on that scale I showed you before with the 1, 2, 3. And the probability of achieving that result by chance is less than 2%. Then whites in the diagnostic condition, and then they give you probability is 0.001. And then whites in the non-diagnostic condition, probability less than 0.025. So in other words, those black individuals who were threatened by saying this is a measure of your intellect, an area that the stereotype poses a threat to them, then they did worse on the test. And you can see the results here. These bars are showing confidence intervals. And so diagnostic people in the threat condition, this is the group that they're referring to. These black students in that threat condition, where that stereotype was activated and created an anxiety-producing situation for them. And you can see that they did worse than this non-diagnostic condition, the non-threat condition for black individuals. And white individuals, that threat didn't influence them, because there's not a stereotype like that. So next we talk about one-tailed and two-tailed tests. So researchers predict something about their sample. They form a hypothesis, and in their hypothesis they choose a direction. They say that their sample mean might be lower than a known mean, higher than a known mean, or just different in some way from the known mean. They're not sure if it's going to be higher or lower. And if they predict that the threatened subjects will perform worse than typical people, I'm giving a general example, then they would be doing a one-tailed low test. So they would think that their sample would fall right into this area. If they predict that non-threatened subjects will perform better than typical people, so people who aren't threatened will perform better, then they're looking for the test scores for that group to be in this high end of the distribution, and that would be a one-tailed high test. For a two-tailed test, they might predict that the test scores of threatened subjects will be different in some way than typical people. And so the test scores could be on the high end of this distribution or on the low end of the distribution, and either way, this would be considered a significant result. Now, if we're using a p-value of 0.05 and we have a one-tailed low test, we would expect the entirety of, we are allowing that sample score to fall anywhere in this range. If we're doing a one-tail high test, then all 0.05, 5%, we can have this entire range, 5% highest scores. But if we have a two-tailed test, we have to divide that probability level in half if we want to keep a p-value of 0.05. So we can see that we've divided it here, and so 25% of the lowest tail would yield a significant result, and 25% of the highest tail would also yield a significant result, but the p-value is divided between those two tails.